Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series presented for the benefit of the BSc Physical Sciences students who are doing the paper on applied electronics. You all know that electronics or applied electronics is nothing but the study of electron dynamics, how electrons move in solids, in semiconducting materials. That gives rise to what is called the semiconductor electronics. Now, we have been seeing how electrons behave in solids to a certain extent. Before that, we should know how electrons behave fundamentally in atoms, and in the previous lectures we started with the Bohr atom model, and then we went to the Sommerfeld atom model. And you may ask the question, why should we have so many atom models? And so in this unit 2, which is coming under this chapter on applied electronics, now we have the vector atom model, spatial quantization, electron spin, quantum numbers associated with the vector atom model, and so on. And hence the contents of this lecture will be as follows: space quantization and allowed orientations, orbital magnetic moment, concept of spin magnetic moment. Essentially, we are trying to understand the vector atom model. As I told you in the last lecture, even if you look at the simplest atom, the hydrogen atom, which Bohr tried to explain, and he tried to make us to understand the origin of spectral lines. We saw when the hydrogen atom, when it is excited, the electron is excited, the electron will come down. When it is coming down, you have series of lines coming under so called Lyman series, Balmer series, Paschen bracket, Fund, and many other series, right? They are in the ultraviolet regime and so on. Now, anyway, I told you in the previous lectures, even the H alpha line, the first line in the Balmer series, could not be explained by the Bohr atom model. Bohr atom model is a simplest atom model, wherein we have got a proton at the center, the electron is revolving in a circular orbit. You know, the electron is revolving in a circular orbit. The point I want to emphasize is, because I am going to talk about space quantization, which I have done to a certain extent earlier. The space quantization means what? Now, in the Bohr atom model, the electron can revolve in an orbit like this, right? The radius is fixed. When the electron is in the K shell, the first shell, the radius of the electron is known, it is fixed. So, the electron is revolving like this, it can revolve in this direction. So, all possible orientations are allowed. So, it can revolve like this, or it can revolve like this 90 degree perpendicular to this revolution, or it can revolve like this, or any angle is possible. Now, what is done by space quantization? Sommerfeld was the first person to talk of this kind of space quantization, restrictions introduced on the path of the electrons. You know, more and more restrictions are now imposed on the electronic motions. Bohr said the electron can revolve only in certain selected orbits. He spoke about the definite radii. The electron can revolve in the first shell, then the electron can revolve in the second shell and third shell. They are called the privileged orbits or non-radiating paths of the electron. But now, the space quantization is introduced. That means what? The electron can revolve in an orbit like this, perpendicular to the plane, perpendicular to this direction I am showing here. The electron can be revolving like this, okay, or it can revolve in this plane, right, that is parallel to the orientation. And so, only certain selected orientations are allowed. Because we are having selected orientations, we talk of space quantization, and we come across many quantum numbers in the vector atom model. Now, what are the quantum numbers? You have the orbital quantum number n, right, then you got L, then S, and then when you apply a field, you assume that you apply a field, then you come across other quantum numbers. So, here as far as the contents are concerned, we have the following sequence, and we have the space quantization. This diagram I have shown earlier. The point I want to make is, if you have an electron revolving in this plane, then there can be another plane perpendicular to this plane. This, you got a plane here, this is a perpendicular plane, then you got a plane inclined, another plane inclined. So, the space is quantized. The electron can revolve only in certain planes, right. There is a plane, there is another plane, and so on. But in the Bohr atom model, all possible orientations are allowed. That is, the plane can be in any direction. Now, by space quantization, there are only certain definite planes in which the electron can be found. Okay, that is a very important thing. So, space quantization. So, when I am talking about space quantization, let us look at this orbit, right. You have got electron revolving in this orbit. So, when the electron is revolving in this orbit, then there will be the angular momentum of the electron will be in this direction, right. The angular momentum of the electron will be in this direction. Therefore, we will define the angular momentum as PL. P refers to momentum, L refers to the orbit, the orbital angular momentum, right, PL. Then, before I go to spin, I am talking about PL, the orbital quantum number. So, L is called the orbital quantum number. The first comes the principal quantum number n, okay, n, then L, the orbital quantum number. Then you come across what is called a spin quantum number. So, how many quantum numbers? N is the principal quantum number, L is the orbital quantum number, third is the spin quantum number. I will come to the other quantum numbers a little later, and also I will not come to spin actually now. I am now telling about the orbital quantum number or orbital momentum, because the electrons are confined to only certain planes, the angles are confined. Therefore, the angular momenta of the electron will be confined to certain discrete values. So, angular momentum is confined to certain discrete values. So, I will show PL will be equal to LH cross, where H cross is the, what is H cross? H cross or H bar is the unit of angular momentum. What is the unit? it is h by 2 pi, right? H bar is h by 2 pi. Now, therefore, the angular momentum vector will be in this direction. If you have got a plane, electron is revolving in this plane, the orbital angular momentum will be in this direction. Then, when I am talking about orbital angular momentum, it should also tell you electron is a charged particle, it is revolving in an orbit. An electron revolving in an orbit is equivalent to a circuital current. You know, electron revolving in a, going in a wire. What is current? Is nothing but a flow of electrons. Now, electron revolving in an orbit is equivalent to a circuital current. There will be, whenever there is a current, there will be associated magnetic field. Whenever there is a current, there will be associated magnetic field. Therefore, apart from this angular momentum vector, there will be a magnetic moment that will be acting in this direction. I will again tell you, repeat the sentence, there will be a associated orbital magnetic moment. This is the orbital angular momentum. The orbital magnetic moment will be acting in this direction, exactly opposite to that of the direction in which the angular momentum is operating. This is the angular momentum vector. Now, exactly opposite to this, there will be an orbital magnetic moment, for the simple reason that electron is a charged particle. A charged particle revolving in an orbit is equal to current, circular current. With every current, there will be associated magnetic field, and then there will be associated magnetic moment. So, we are trying to understand in short, in a very detailed way, the manner in which the electrons behave in atoms. Here we will come across many quantum numbers. As we proceed, we will understand. In the vector atom model, the orbital angular momentum of the electron is given as PL is equal to LH cross. So, PL, the definite orbital angular momenta, are nothing but LH cross. So, what is H cross? As I told you, is the unit of angular momentum. L is what is called the orbital angular momentum. It is orbital angular momentum or orbital quantum number. L is the, N is the principal quantum number, L is the orbital quantum number. This orbital quantum number will take values starting from 0 to L, 0, 1, 2, 3 and so on. I will come to the details later. So, you have got the electron is in 3 dimensions. Space quantization requires 3 different quantum numbers, N, L and ML. So, the energy of the electron depends upon all these things. So, I mentioned to you about the orbital magnetic moment. Apart from the orbital angular momentum, there will be a orbital magnetic moment. As I told you, that will be exactly in the opposite direction. Supposing the momentum vector, the orbital angular momentum vector m is in this direction, there will be a magnetic moment which is exactly opposite to this direction. Okay. So, that we have to calculate the current that will be associated with the electron movement, and then what is the orbital magnetic moment that will be associated with the orbit in which the electron is revolving. The discrete orientations of the electron orbit with respect to the reference magnetic field direction. As I told you, you apply a field and assume that the field is reduced to 0, because you need a reference frame, a direction is needed. So, reference magnetic field direction occur due to the interaction of the orbital magnetic moment of the electron and the reference magnetic field. Since the electron has got a negative charge, the electron revolving in orbit is equivalent to a circular current, then there will be a magnetic moment, right. The direction of the magnetic field is given by the left hand thumb rule. The magnetic field, you know, you have got the left hand thumb rule, you have got the current, the applied magnetic field and the motion of the conductor. The left hand thumb rule, the rule says the direction of the orbital angular momentum I showed in the slide. I told you the direction of the magnetic moment is exactly in the opposite direction, that of the orbital angular momentum. As I told you, we have to calculate the magnetic moment that is possessed by the electron because of its rotation. It is revolving, right. You got a revolving. So, the electron should have an orbital magnetic moment. Let us have a break at this point. Welcome back after the break. I told you that we need a detailed understanding or an in-depth understanding of the electrons and atoms in order to explain the experimental observations which remain unexplained, namely the fine structure of the H alpha line or H beta lines, and not only that, the Zeeman effect and the Stark effect. These are some of the experimental observations which demand proper explanation, which are not forthcoming from the Bohr atom model and Sommerfeld model, and this led to the vector atom model, in which we introduced what is called a space quantization, because the space is restricted and still the electron is revolving in certain specified planes and specified orbits, and we want to calculate the orbital magnetic moment. We calculate orbital magnetic moment using the Ampere's theorem, which says that magnetic moment induced will be equal to the current times the area of the loop. A is the area of the loop and I is the current. So, mu is equal to I into pi r square, where r is the radius of the circular orbit. You have got an electron revolving in a circular orbit. Therefore, the magnetic moment of the electron due to the orbital motion is given as mu suffix L. L refers to the orbital quantum number. Remember, L is the orbital quantum number. We introduced the principal quantum number and then the orbital quantum number L. So, mu L will be equal to I into A. What is current I? I is nothing but the rate of flow of charge. So, charge divided by rate means time. So, I will be equal to E by T. A the area of the loop, because the electron is revolving in a circular orbit, the radius of the orbit will be r. So, the circumference will be area of the orbit will be pi r square. So, r is the radius of the electron orbit and t is the time period of electron revolution, but this 2 pi r by t will be equal to velocity. Velocity will be 2 pi r, that is the angular velocity divided by time taken, will be equal to the linear velocity v. We will substitute this v here and you write mu L will be E pi r square into v by 2 r. You have your pi r square into E into 1 by t. 1 by t is coming here. So, 1 by t will be v by 2 pi r. That is what I am substituting here. In the place of 1 by t, you have to substitute v by 2 pi r. That becomes E v r by 2. So, using P L equal to m v r into the above equation. What is P L? It is the orbital angular momentum. P L is the momentum, it is the moment of momentum. Angular momentum is nothing but the moment of momentum. M v is the momentum and r is the radius. So, the moment of momentum is m v r. You know, in the Bohr atom model you write m v r. The expression for the orbital angular momentum is m v r. So, that is what I am finding here, writing here, that is the moment of momentum, that is m v r. So, my mu L will be equal to E by 2m multiplied by P L, and this E by 2m will be here. Then P L, you know what is P L? P L we had as LH bar. We had P L equal to LH bar. P L is quantized, right? P L is LH bar. So, we introduce your P L here. So, your value becomes now E by 2m into LH cross. What is mu L? Mu L is the orbital magnetic moment, because of the rotation of the electron, revolution of the electron in a particular orbit. The electron is now associated with a magnetic moment, and this magnetic moment will be quantized. How do you say it is quantized? Because you see here the expression mu L will be E by 2m into LH cross. E is fixed. The charge of the electron cannot be changed. We saw how the charge is measured by millicon. Mass of the electron is a constant. H bar is h by 2 pi, the Planck's constant divided by 2 pi, that is a constant, and L will have only certain different values. L will start from 0 to 0, 1, 2, etc. Therefore, L is fixed. L is the orbital quantum number. We will take only integral values. Therefore, they are all constants. E, 2m, L, H bar, they are all constants multiplied by L. L will take integral values, because L takes integral values, mu L will take integral values. So, the orbital magnetic moment will take integral values. That is very important, right? We are in the realm of quantum theory, you are using quantum ideas, therefore, mu L will be in terms of expressed in terms of L. So, mu L is quantized. All the symbols on the right hand side above equations are atomic constants. So, you write mu L will be equal to, you have take this H bar here, LH bar here, mu B, what is mu B? E by 2m is mu B, and this becomes the unit in which the magnetic moment is expressed. The E by 2m or E by 2mc is called Bohr magneton. Bohr magneton is a unit of magnetic moment. In atomic physics, the magnetic moment is expressed in so many Bohr magnetons. One Bohr magneton is nothing but Eh bar by 2m. When you go to nuclear physics, you talk of nuclear magneton. Here you talk of Bohr magneton, where m is the mass of the electron. In nuclear physics, that mass of the proton will come in the denominator, or mass of the nucleon in general will come in the denominator. It is called a nuclear magneton. So, the numerical value of the Bohr magneton is given here. So, the magnetic moment in solid state theory or in atomic physics will be given in terms of the Bohr magnetons, the ratio of mu L and P L, that is the magnetic moment divided by P L. You know, the mu L is the magnetic moment, the orbital magnetic moment by orbital momentum, right? Magnetic moment by orbital momentum, that becomes equal to E by 2m. It is called gyromagnetic ratio. It is now G is written as G is equal to small g into E by 2m, and this G is called a Landé splitting factor. G will be equal to 1 for orbital motion. So, G will be equal to 1 for orbital motion. That is important, right? Now comes, so far we have been talking about the revolution of the electron. The electron is revolving in certain specific orbits. Now, two Dutch scientists by name Uhlenbeck and Goudsmit came into the picture. They said that the electrons should be considered like our mother earth. Earth is revolving around the sun. Not only the earth is revolving, but also it is spinning, right? Earth is revolving and also it is spinning. Therefore, they attributed these aspects, whatever that we have got for celestial objects, they attribute to the electron. They talked about the electron spin. The spin concept was introduced by Uhlenbeck and Goudsmit. Therefore, the electron, which is supposed to revolve in a circular orbit according to Sommerfeld or the vector atom model, apart from the rotational motion, the electron also will be spinning. So, let me not go into the details, but you know, you consider the electron as a wave at a later date. So, do not ask how the wave will be when spinning and so on. So, let us now assume the electron is a particle, the particle is revolving. Apart from the revolution that is associated with the electron, there is a spin motion also. The electron is spinning, and if it is spinning, then it will have a spin momentum and also a spin magnetic moment. So, according to the thing that was introduced by Uhlenbeck and Goudsmit, the electron revolves about its own axis while orbiting around the nucleus. Apart from orbital motion, the electron is endowed with a spin motion. The concept is very much akin to the spinning of the planets of the solar system, similar to your PL equal LH cross. That is what we wrote. The PL is the orbital angular momentum is equal to LH cross. Similarly, now we write the spin angular momentum is equal to SH cross. What is S? S is known as spin. You write S is equal to half. S is equal to half. When we ask the students what is the value of the spin of the electron, they will say S is equal to half. What is half means what? Half a rupee, of a dollar, and so on. So, when you say make a statement that the electron is having a spin is equal to half, that means the spin angular momentum is of H cross. The spin angular momentum, the angular momentum associated with the spin motion is equal to half H cross. H cross is the unit of angular momentum. Now, apart from the spin angular momentum, as we had in the orbital angular momentum case, we had the orbital angular momentum and also the orbital magnetic moment. Similarly, we have got a spin angular momentum and a spin magnetic moment, right? There will be a spin magnetic moment will be there. These two magnetic moments ought to be summed up. Now, before we sum up the magnetic moments, the angular momentum, the orbital angular momentum and the spin angular momentum themselves ought to be summed up. They ought to be vectorially added. One is so that results to in what is called the resultant angular momentum G. You have got a orbital momentum L, then I introduce the spin momentum PS. One is PL, the other is PS. Now, PL is written as LH cross, PS is written as SH cross, whereas half, that is called the spin angular momentum. The PL is the orbital angular momentum. Now, I talk of the addition of the two momenta, the orbital momentum and the spin momentum, okay, as both orbital angular momentum PL and the intrinsic, it is called intrinsic, right, intrinsic spin angular momentum PS that determines the state of the electron, both are quantized, they can be summed up, they are added vectorially, they are added, and you have got the allowed orientations, right. And regarding spin, I can talk of the magnetic spin quantum number. When we say the electron is having the spin half, then when you apply a magnetic field, it can either spin up, either it can have a alignment of spin along the field direction or opposite to that of the field direction. Therefore, if you say S is equal to half, I can say the MS, the magnetic spin quantum number. So, the spin quantum number is half, spin is half, but when you apply a magnetic field, then I will be talking about the magnetic spin quantum number, and that will be either plus half or minus half, depending upon the fact that whether the electron is spinning itself or the spin momentum is parallel to the field or anti-parallel to the field. If it is parallel, it is plus half, anti-parallel, it is minus half. Okay, you apply a magnetic field. This is the magnetic field direction. Okay, it may be half H cross or minus half H cross, depending upon the fact that so the spin magnetic moment will be momentum also will be given as ms into H cross, and ms will take two values plus half and minus half. Let me now pass on to the summary session of this lecture, which goes as follows. The orbital motion of the electron gives rise to the orbital magnetic moment. Similarly, the spin motion leads to the spin magnetic moment. Both orbital magnetic moment and spin magnetic moment, both of them are quantized, and the questions which I am posing to you are: 1. Give the magnitude of the allowed orbital momenta. What is meant by spin of the electrons? Give the magnitude of the orbital magnetic moment. What are the spin magnetic quantum numbers? With this, we come to the end of this lecture. In the lecture to come, we will see more quantum numbers in the vector atom model. which will be made use of to find out the number of electrons in a shell as well as in a subshell. With this we come to the end of this lecture. Thank you.